Okay, so the stage is yours. You can start.
Thank you very much. So, yes, I rather would be in Prague today, but unfortunately it was not possible for me. So I'm missing it anyway. So let's start with the presentation, which I have prepared for you, where I will show you some cool stuff, which is in Optistruct. For those who don't know me, I'm Marian Bulla, located in Germany, former Altair. Now, after the acquisition by Siemens, I'm Siemens. Yeah, I'm in charge with the software for engineering solvers. And today, now, I will speak a little bit about Optistruct Implicit, so Simcenter Optistruct. I will not go into details for explicit. For those of you who are interested in the explicit features, I have also a second presentation today afternoon, which will deal with radios and the new capabilities there. But here some cool things from Optistruct. Anyway, let's start from scratch, from begin. So Simcenter Optistruct workflow, for what it is used for. So the goal which we have is having just one model for one solver. So solving all the individual things which you see, NVH, linear, static, where I will show you some examples, transient model things, and of course optimization features. For sure, also for stresses, fatigue calculations. So this is already all possible today in Optistruct, which was also the case in the past years. So now new stuff, which is maybe not new, but what you also can do is coupling. So where we are also enhancing the capabilities. For example, you can couple it with motion solve to see these kind of events, the driving vehicle and the hit of battery casing on this obstacle, on this bump on the street. So these kind of investigations you can do where you see then the strains, plastic deformation or whatever stresses, forces acting due to this kind of let's say coupled solution with motion solve. So this is possible today. Anyway, so beside of that, you can do also manufacturing solutions with this, which is state of the art, this kind of intrusions, nodal, normal modes, global lateral forces, and so on. So this is also state of the art where you investigate the thickness change from stamping, for example, or introduce plasticity and carry over these results for further applications for crash, for example, or other things. So other solutions which are also existing beside of Optistruct in terms of manufacturing. So this is, for example, for casting, which you can see here, or stamping, or extrusion, injection molding for polymers, or welding, or 3D printing, or polyurethane foaming for these seat cushion foams. So these are also, beside of Optistruct, available in the HyperWorks portfolio. Okay, coming back to the solver point of view. So for event time magnitude, which we are talking about, is here in implicit domain, which means slow events, creep, static. Then we move to a little bit faster, quasi-static, even more faster drop tests. So for crash, and then going to higher velocities, impact, hypervelocity impacts. Optistruct is located here in this area, implicit as a pure implicit solver. So dealing with NVH, the eigenmodes or force transfer path analysis and so on, these things are the main domain of Optistruct. For going further, faster in velocities, we have Simcenter radios, which cover the faster events and higher deformations up to fracture and damage, which I will talk today afternoon a little bit more about these features. So like these events here, car crash or aero industry, so bird impact. Nowadays also these kind of defense applications and the hypervelocity things which are in space where you don't have the effect of air. So this can be covered with Simcenter radios. Anyway, Optistruct has now been enhanced by the capabilities for Implicit, so you can also run drop tests and these kind of things with Optistruct already right now. So let's go now a little bit back to some examples to prove first, if you are new to this domain, just to prove the accuracy of Optistruct. So where I created this first validation test, which is a very simple cantilever beam, which you can compute the deflection here analytically, which you have learned in high school or whoever in kindergarten. So this is very simple equation, which everyone can solve, where you know the solution, for example, by this geometry, you know the deflection will be 1.9 millimeter. So this is a very simple case. And to prove if the solver is delivering the right answer, I did just this very simple test. Used Optistruct, applied the forces here and applied and checked the results, which are applied within 1 second. You will get these results or even faster. So this is more or less instantaneously this kind of simple model, and you see it matches exactly with reality. So this is the first step for validation, a very simple one, and I'm pretty sure you already did it. If not, I can send you this model or can show you how to create it. It's straightforward. So now then we did something more complex, created this kind of body in white at the University of Applied Science in here in Germany. So we built this vehicle structure out of steel and then measured the deformation and deflection by applying the forces here and here by bending, also torsion and other load cases. And just to check if this fits or if we can reproduce these results in our FE models. So here I used Optistruct. I meshed this geometry. We created the same model as it was I showed you from the original photos. So, and then checked the mass. We measured the mass in reality and in the FE model, which delivers the same results as 10.7 kilograms, which is a small model, but perfectly suited for this kind of validation. Yeah, and then what we did now is also check the stiffness by applying different levels of forces or mass on our structure. And we saw from test the blue line and the simulation delivers the orange line. So you see it's almost a perfect agreement. So if you want, I can send you this model, and the real world test case can also be achieved. So we have this real test example, so I can provide it to you if you are really interested. So we can talk about that. So it is available, both the FE model and the real world exercise. Then we checked also the eigenmodes for bending and for torsion, so the other higher order eigenmodes. And then for sure we wanted to reduce the weight. So we initially were thinking, okay, let's reduce the material from steel to aluminum, which is a good idea to reduce the mass of all that stuff. And it worked perfectly well. So from 10.7 kilogram, by reducing the material to aluminum, we can reduce it by more than 50%, which is good. But for sure, the stiffness drops. So, and this is not good. So, and here we wanted to have a kind of solution how to improve this situation by keeping or at least having a reduced mass. So then we started, or I started to think how to do it, how to optimize it. For sure, the floor plate would help here to increase the stiffness and some other enhancements, but it will bring a lot of additional mass here. So I did an optimization here to reduce the mass by keeping the stiffness. and the final shape, final geometry was figured out like this. It looks quite fancy, so I was a little bit surprised. I double checked it, and for the bending case I add these additional beams here, so we have to add a little bit mass to improve the stiffness by after exchanging the material from steel to aluminum. So, and the result were also double checked for the eigenmodes, which means for the eigenfrequencies. And after the optimization efforts, I was able to increase the stiffness now to meet the stiffness of steel. The same for the torsional stiffness. But the mass is still a little bit increased to close to 7 kilograms, which means a total overall reduction of 35% versus this very simple steel frame. So, and this is usually how the workflow is done in the industry by these kind of material substitutions. Okay, going further into the new features, which is now new in terms of optimization, because I did here, my example was using Optistruct, where I did the optimization of the floor and other things, which I will not talk about deeper here. So I did it now, and with the new version of 2026, Optistruct has the capability of mesh refinement during the optimization procedure. So, and this is new, and this is a really very, very cool feature, because you do not need to start with a very fine mesh, which takes also a long time being solved in Optistruct. So you can start with a coarse mesh. So this is then the motivation for having this technology now, to get more detailed results, to reduce the solution time, because it's somewhere between the coarse mesh, which you can see, the initial mesh, and if you would use a fine mesh, it would take very, very long time for the entire optimization. So now the solver is able to define its area and refine the mesh during the simulation. So the coarse meshes are so used for this purpose, use the coarse meshes, but internally and automatically refine them iteratively based on topology optimization results. So it is refining the mesh where it needs a little bit more details. So, and this is done in a kind of continuous approach during one simulation. So the user can select which topology regions have to be refined. The user can see optically the selected conditions to trigger refinement. User can select the number of refinements, 1 or 2 or more available. So this is now a limitation only for 3D elements, so hexas and tetras. The next one will come in near future. So this is really, really fresh, and it's you have to do some things. So optional configuration files to customize model parameters for challenging problems, e.g. boundary conditions or constraints, can be set to different values or different refinement levels. So, and again, this is automatic mesh refinement during the simulation. Here, for now, it's now being implemented in HyperMesh. So in the current version, it is still not available. It will come in the next version. So please be patient a little bit. Anyway, you can add this card. So this is how I did it. I added with my text editor this card, and then I had the possibility of doing it, because Optistruct itself is already to deal with the mesh refinement. So this is how it looks like. Then you start with the coarse mesh, and then the first topology will be created, then the refinements will take place, and then you have the second level of refinement, which will go into deeper, finer structures and results. So this is what you would see then. So I created also a sample model, but first here, these are the models which you can already see how the refinement works, starting with the initial coarse mesh, the internal regions which should be kept by the solver. They are going to be refinement in the first stage, and then in the second step even more. So you will get a really nice structure out of it. So just to show you how it works, I created here very, very simple cubic, constrained it on the back area and applied one force to see how it looks like while it is working. So objective is for sure to reduce the mass here, but it can be anything else. So you have plenty of possibilities, but this is just to show you how it works. The result of this looks like that, this model. So it is not very nice because it's quite coarse. You can for sure smooth it. So if you smooth these results, it will look like this. Anyway, not very nice because I wanted to have this coarse mesh because it's running very fast in the optimization. And this is the remaining structure after the Optistruct optimization. So smoothed results with the coarse mesh, still not very nice, but much better already. And now if I switch on the automatic refinement of the model, so I'm obtaining something like this. And this is now much better to see the final results with internally refinement during simulation. So this is the results which came out of this very coarse model, because initially it is very coarse, and this area which may remain will be refined in the mesh. I used here also 2 levels of refinement, and this is what remains. Again, compared, for example, with the initial mesh, which looks like this, and the initial final result, which looks like that. So this is really a breakthrough which we have now with this automatic mesh refinement during optimization. So next feature which I would like to introduce you is AI, the automated machine learning strategy in Optistruct and HyperMesh, which we have embedded in HyperMesh already, which you can use. So for physics AI, you can switch on this menu and you will have access to these parts where you just need to create a project folder, then your simulation results, which means you have to train your AI model, the physics AI, with a lot of data. And I will show you, of course, one result. So, and here you have the data set, which will be fetched by physics AI to train the model. And then you need to train the model. You will obtain a model, a trained one, and then test results. And once you have a trained model, you can produce the results almost immediately with one click. So in almost real time, once the model is trained. And here I show you a video showing this. This is available in a beta version of HyperMesh, so it will come soon. So this is real time now video. We trained a model for a bracket, and then you just need to add the mass here. How much mass do you want to have? Then generate almost immediately by one click the final result by a trained model. Now you can play a little bit with it, which means you can change the connection areas, the connection points to a different area and regenerate it by just one click. Immediately you will get the final results by the artificial intelligence and machine trained model. So, and as you can see, it works almost on click. So you can play now with different sizes for this kind of model, which is a very simple one, but it already demonstrates how fast it generates now results by using the AI model. And this is really the future, at least for very fast design explorations, which is almost in real time and really, really fast. So this is where we think the engineers can use the AI. For example, if you want to reduce the mass even more, it will provide you even final structure here. And the usage is then with the trained model almost in real time, which you can show then during whatever presentations or within in front of your management or your colleagues. So and this is something which really increases the speed, the performance of the models, and this is the future which you see here now. So this brings me almost to the end. So conclusion, today's presentation has shown advanced the power of simulation and validation compared to reality with Simcenter Optistruct. These capabilities are helping engineers to dramatically reduce the development time and costs by using CAE. And with latest developments of Simcenter radios, the engineers are getting results in much higher quality, which enables them to increase the results fidelity. And last but not least, AI, machine learning tools help the engineers to drastically reduce the development time. And with that, I would like to thank you for your time and your attention. Open for questions.
Thank you, Marian. Thank you. Looking forward in 1.5 hours. But now, as you said, time for question. You have nothing asking. So Marian, no questions.
Yeah.
So as I said, we are looking forward in 1.5 hours.
Perfect. Thank you very much for your time and see you in 1.5 hours.
Thank you for your time. Bye-bye.
Thank you. Bye-bye.